We're doing number 9 in 2002. D is a bad answer because if I do this as number 1 and 2, if I draw these carbons like this, right, the p orbital, right, carbocations are an empty, we want to have them be an empty p orbital because that way it can stabilize it by resonance. In this case, right, the hybridization state of carbon 1 is sp2 hybridized, which means it has a p, an sp2, sp2, and an sp2. The pi bond's still there, right? And what kind of bonds make pi bonds? P orbitals. So that automatically checks that one off. So the only thing that can be empty is one of these sp2s. And so this is the one that's empty. And so you can't stabilize that at all with resonance, right? So that's why that's not a good answer, right? But usually what happens is people narrow it down between those two. So what's the best answer going to be? A, because A, then you can do resonance, right? You want the carbocation next to the pi bond or next to the lone pairs, right?
Maybe like secondary benzoic, right?
Secondary allylic, not benzoic. Yep. So A, right? You want something to be allylic or next to the pi bond, right? You don't want the plus. You want the empty orbital next to the pi bond, not on that carbon, right? So let's get number 3 in 2002. So the question here is, which compound absorbs at the longest wavelength, the lowest energy in the UV spectrum? So what are we looking for here? We're looking for conjugation, more or less? More, right? So whatever one's the most conjugated. So which one of these is the most conjugated, actually? Looks like it's D, right? D has, let's see, make sure. D has 3 pi bonds conjugated together. Yeah, it looks kind of weird, and that's kind of what they're going for, to see if you really understood, right? You can see there's 1 pi bond, 2 pi bonds, 3 pi bonds. Again, the same kind of question as we just did, right? These pi bonds, right? All these p orbitals are all lined up next to each other, right? And the more they're lined up like that, the easier it is to go from pi to pi star. That's what UV vis is, right? So colored compounds have lots of pi bonds, right? So that means longer wavelengths, lower energy, right? Easier to go to pi star. The other ones, they all have at most 2 pi bonds next to each other, right? So 3 is better than 3 in a row is better than 2 2s. That's basically just here, right? So something like if you look at this is D. So if you looked at, let's say, B. So that's B, right? That kind of. So there's B. So we have pi bond, 2 of them in a row. Pi bond, 2 in a row. But 2, even if it's not additive, you want more conjugation, more pi bonds lined up, the better, right? So 3 is still better than 2 2s.
Why does that absorb at a lower energy instead of a higher energy?
So lower energy, right? Because so it's pi to pi. Because as you get more and more pi bonds together, the pi to pi star transition to get the electron excited actually gets less and less. The HOMO-LUMO gap, right, gets less, right? So it's easier to go from pi to pi star. Let's work on this one. So number 18 in 2002. So this is a equatorial axial problem with chair conformations. Right. Right, so they're trying to get you to look at, basically the end thing you need to remember is when things are equatorial, like sticking out in the equator, it's lower energy, right? So when things are axial up, they tend to bump into other things that are also up. There's more in the way, so, right? So they want a lowest energy conformation here. You want to get the things equatorial. You want to get the things going right towards the equator, not up or down. Right, so these are all, I'm drawing all the axial ones in here. right? And these would all be the equatorial ones. Right, so you want things equatorial. So if you looked at this, if you knew that right away, the trick was they were trying to get you to think about cis and trans, but it's not a cis-trans question. It's an equatorial axial question, right? So actually C is the answer, I think. Let me see. Yep, C is the answer, right? And that's one where you have your CH3 and your CH3 both equatorial. And that means the lowest energy conformation you can get. Right? So basically all you're looking for here is things not being axial. Right? So A has one axial and one equatorial, and so does D, one axial and one equatorial. Whereas C has them both equatorial. That's what you want. Let's do number 5, 2002. So the question is asking them, which compound is not aromatic? So you're going to need to know is, what are the rules for aromaticity? What are the two things you need for aromaticity? An odd, what?
Odd
Number of pairs of electrons. What's the second thing you need?
uninterrupted.
An uninterrupted yep,
Orbitals.
pi bonds. Uninterrupted pi system. Uninterrupted pi system. Which basically means what hybridization state can it not be? Cannot be sp3 ever. And so then it's pretty easy when you look there and say which one of those for number 5 doesn't qualify for this. A, right? So they show
On number 8, are those lone pairs of sp2?
these lone pairs would be in the p orbital probably. This nitrogen would probably be sp2 hybridized, maybe.
So it's
So it can still do resonance, but
This one is
sp3 hybridized carbon, not an uninterrupted pi system.
so it's
Where-
those are
that
So C, so if you look at C, yeah, that nitrogen is sp, right? It chooses to be sp2 hybridized because it allows it to make the compound
more stable.
aromatic, right? More stable. Right, so those lone pairs, right, are going to be in a p orbital. That nitrogen is going to be sp2 hybridized. Now contrast that, so that's parole. Contrast that with your old favorite, and mine too, pyridine. Right? Again, you know how I harped on you guys about these molecular orbitals, right? What's the hybridization state of this nitrogen? It's sp2 hybridized, right? What molecular orbital are those lone pairs in? sp2, right? Because it only has, if it's sp2 hybridized, how many p orbitals does it have? One. And what kind of bonds, or what kind of orbitals form pi bonds? P. So it's only one, so it has to be an sp2, right? Every p orbitals form pi bonds until next year in advanced organic. So for number 22 and 2002, they're saying, what's the best way to form this product? Essentially, right? And the starting materials they're giving you are strong bases and an alkyl halide, right? They're giving you a strong nucleophile. They're giving you alkyl halide, alkyl X, plus an OR minus Na plus. Right, so that automatically should tell you, right, SN2 reaction. Right? If I have a strong, it's not an elimination because there's no pi bonds in the product, right? So it can't be E1 or E2. And your nucleophiles, all your possible products, all are OR or O with next to a sodium, right? So it's O minus. So it has to be an SN2 reaction. Right? So what are your rules for SN2 reactions? What kind of alkyl halides react for SN2? Primary. Just primary. Right, primary and secondary? I say primary and secondary? Yeah, primary and secondary. So for SN2, it's only going to be primary and secondary alkyl halides, right? So that means we had to break, right? When I look at the bonds, I'm saying it must have came from this, right? This must have been O minus, and this carbon must have been bonded to an electrophile, right? Or, excuse me, a halogen, right? Iodine, bromine, or chlorine, right? So now I look at your answers and say, okay, which one has, right? I can't have an alkyl halide that's anything, primary would be the best. So which ones can I eliminate right away?
A and D.
A and D, right? Because those both have tertiary alkyl halides, right? So those won't react in an SN2 reaction. So now you got a 50-50 shot. Now between B and C, right? Looks like the nucleophile is the same in both, right? What's different?
Leaving group.
The leaving group. So which one has a better leaving group?
C.
I, right? Iodine's better leaving group C, right? So the best way to do this is with O and A plus CH3I. Right? Those are the best starting materials to do this.
Why don't you pick SN2 versus SN1?
I have a strong nucleophile. I can't be SN1, right? If I have O minus, that's why they didn't. Notice how they did this, right? They didn't put O minus and A plus. They put O and A, right? But if you see sodium or lithium, right, those don't form covalent bonds. They form ionic bonds, right? So just because it looked like this, you should recognize it as O minus. If you see minus, you can't have carbocations, right? So for this one, so number 26, 2002. Page. But again, here's a NO2, right? So NO2 has a overall negative charge here, right? HCl is in there. So what this does, right, which I don't know if I showed you the mechanism of this, but I did show you this happens, is that this is the way you turn that into this. You do the diazotization, where you make basically an N2 on your benzene ring, right, which is a pretty good leaving group. And so then whatever you add in, right, copper bonded nitrile, we just talked about this, right? The metal, how the plus charge, the nitrile is a negative charge, and you can just replace the leaving group with whatever you want to add, whatever nucleophile you want. So you end up getting this product. So if we're doing number 27 in 2002, first thing I would do is draw out 2-methyl-1-butene. So butene, right? 1-butene means the double bond is that carbon 1, 2, 3, 4. 2-methylbutene, that, right? 2-methyl-1-butene is that molecule. And they're saying which reaction provides the best synthesis of this, right? So the first thing you gotta remember is how many different ways do you want to make alkenes, right? You can make alkenes from triple bonds, right? We've reduced triple bonds. What was the first way we learned? What kind of reactions was it? Eliminations. And then most recently we learned how to make alkenes another way. The Wittig, right? So if you look at your answers here, you'll see, right? B has a ketone and then NaOH minus, right? Which doesn't form a double bond, right? It doesn't get rid of the oxygen. You look at C, and there's an alcohol and strong acid. Now that can do eliminations, right? We talked about that, tertiary alcohol. And the other one has alkenes and H2 palladium on carbon. That doesn't give me alkenes, right? That gets rid of alkenes, right?
What about the one equivalent?
One equivalent, I don't know what, but
I've never heard of
that
that.
it'll get that more or less substituted alkene anyway. It won't make that. No.
It won't because it's more.
It'll go after the more substituted alkene.
Why?
That's the most electron rich. So I didn't get a chance to show you that too. For 27, right? Right. One of the reasons why 27 doesn't work is because which one of those alkenes is the most electron rich? The one with the most hyperconjugation, which would be the one that's the most substituted. So that would be the first one you'd reduce.
Least stable things.
The least stable, but it's the most reactive. It's stable, but it's most reactive. So basically, it comes down to the Wittig and the H2SO4, A and C. So which one would work the best? So there's a key point here about Wittig that made it useful. What made Wittigs useful? Non-Zaitsev. So if you look at this alkene, right, you can imagine, right, if you drew out C, you get the Zaitsev product, right? Because carbocations, you always get the Zaitsev thing. So that's why it's A, because the Wittig reagents can give the non-Zaitsev products. Right, that's the key. Just to review meso compounds. Here's what we'll call it, Josh. Has an internal mirror plane and has asymmetric centers, right? So it has asymmetric centers, but the molecule itself is not chiral. So it has carbons that are RS, but the molecule itself is not chiral. So something like this, right? Mm-hmm. Each of these carbons has 4 different things bound to it, right? So they could be RS, but the molecule has a line of symmetry, a mirror plane, right? That mirrors itself, so it's a meso compound. The other one I showed you guys a lot was the bromines, right? Usually they're cis, right? They have to be cis because they have to be mirror planes, right? Looking at each other. So things that are cis, like in rings like this, can a lot of times be meso, right? Again, there's that mirror plane, right? Internal mirror plane with asymmetric centers, that's a meso compound. It does not rotate it does not rotate light.
It turns it one way and then it turns back the other.
It just doesn't rotate. It's net neutral for light rotation. So, number 58.
Both accomplish the reaction sequence?
Nope. So here's why. So if we've narrowed it down, NaH, of course, means Na would have it's an ionic bond. Na has a plus charge. H has the minus charge, so it's a nucleophile. It takes the H. Right, we make H2 gas. We have an O minus. We've lost H2 gas. And now we're going to add in an epoxide. Right, so if O minus is the nucleophile, the epoxide has to be the electrophile. Does it matter which carbon of the epoxide we attack? Nope. So let's just pick that one. Right, like an SN2 reaction. Right? And now the next step they do, right, they add in this, right, another electrophile. So this O minus attacks, kicks up. So it's very similar to what you want. The problem is the O from the original alcohol is still on there, right? That's why A and C are the two best answers, but C is the better one. Right. 59. Let's do. I'll do. I'm gonna do 59 first. Let's do 59 from 2002. So this has to do with knowing our strong acids, right? So it'll say H2SO4 and heat, but you guys see that and automatically say H2SO4 is sulfuric acid. That just means H plus, right? That just means H plus. H2SO4, HCl, HBr, H plus. So that's, if you have H plus, that's always going to be a electrophile, right? So whatever's nucleophilic, in this case the lone pairs of the oxygen is going to attack that. All right? So what we've done here is we've turned our alcohol, or OH, which is not a very good leaving group, into water, which is a good leaving group, right? With H2SO4. Tertiary carbon, so we can easily kick this out. So now we have a carbocation here, and we have a choice, right? We're talking about the alpha H's, right? How many types of alpha H's are there for this carbon? For this carbocation, is how many different types of alpha H's? 3. All right, there's 3. There's here, here, and here. So how are we gonna? Which way do we want to have the double bond? Right. So it's conjugated. Right. That's it. All right. Remember, with H2SO4, we can do these eliminations. Right. So you always want a double bond to be conjugated.
What is that like for solution?
Yep. Number 57, 2002. Right? And you have AlCl3. So everybody should see this and know this is a electrophilic aromatic substitution, and it's an acylation. So we put the ketone on. Right? Once we get the ketone on, we have this zinc HCl stuff, which we should all recognize as one of the 3 ways to reduce benzylic carbonyls. Right? H2 palladium on carbon, Wolff-Kishner, and the Clemenson reduce carbonyls that are benzylic. So you'd have that. And the last thing is Br2 and light. And that, of course, does benzylic brominations. So, number 37, 2002. Right? The key point here is there's heat. So that's going to be really forcing conditions. So what is going to happen or could happen, at one point, these are all equilibrium arrows, is you get that attack. And you'd form a tetrahedral intermediate. Right? Tetrahedral intermediate, if you have any good leaving groups, they'll leave. We could sometimes kick out the OH, but that just goes back to where we started. So let's say every so often we do this and kick that out. Even though the nitrogen doesn't want to have a negative charge, it'll be clear in a second why it's more likely that that'll happen, or if that does happen, we kind of get stuck. Right? So now we just made a carboxylic acid with a nitrogen with a negative charge. So you can imagine nitrogens are pretty good bases, right? And carboxylic acids are acids. So if you ever made that, you could notice the one-headed arrow now. You're stuck, right? So the way these equilibrium reactions work, right, is that even if this is really unlikely, right, at some point it should be taking away this H first. But if you heated it up enough, every so often this first step will happen. Then every so often the second step will happen. But then if I ever get this far and this happens, it's over. Right? Right? It's like saying I need to flip a quarter and get heads 3 times in a row. Right? If I have 100 quarters, I have to flip heads 3 times in a row, then I put that quarter aside. Will eventually that happen? Eventually, it might take a really long time, but eventually it's going to happen. So even if this reaction is very unlikely and this one's very unlikely, if I ever get to this point, I make this, right? Because now this is really stable because now this O minus has resonance, right? And you're just stuck. It's over, right? So it's one of those things where, yep, this shouldn't happen. This probably wouldn't happen first. Yep, it probably wouldn't happen first. You're right. And this probably wouldn't happen. Why would it want to kick out an N minus? Exactly right. But if it ever did, and it does sometimes, and you make this, right? You made a product that's so stable that now the equilibrium arrows don't matter. Let's look at number 36 in 2002. So this, we have the alpha beta unsaturated ketone, which we always know is going to be the electrophile, right? Oops, should be an oxygen there. We have this diester. right? And we only have two of these things. It makes it more acidic in the middle, right? Because there's resonance for it, possible for it. So when we treat it first with this base, NaOET, notice how this OET is picked on purpose because even if it did attack the carbonyl and kick out, you'd have the same leaving group, so that's the reason why they picked that. So it acts like a base, has a negative charge. It takes the H, forms the enolate. That enolate is it's a weaker nucleophile, weaker enolate because it's stabilized by resonance, so it attacks not direct, it attacks conjugate in a conjugate fashion. So let me draw that. So it attacks there. You can say these electrons go right to that carbon. That's fine.
Isn't there something there? Isn't there supposed to be a methyl group?
Oh, my bad. Lost a carbon. Methyl. Right? So, I mean, I like to number my carbons. 1, 2, 3, there's 4. These are the ones that are involved. And 5. Alright, so which two new carbons formed a bond? 5 and 4. So I draw 5 and 4. There's 4, there's 5. 5 had a methyl on it. It was also bonded to this OET and bonded to this other OET. 4 was bonded to these methyls. It was bonded to 3. Which is bonded to 2, which is bonded to 1. 1, 2, 3. And looks like 3 has the negative charge. That's cool. It'll get protonated, right? We made this guy in the process in our first step. So it takes that H. Cool. So we have this big old beast of a molecule. It's up here, it's up there. And that's step 1. All right, step 2 up here was H plus or H3O plus. And I'm guessing heat. And it's telling us we lose CO2. Right? So the only way we can lose CO2 is when we had carboxylic acid. So that means we must be turning both these esters into carboxylic acids. All right, so both these esters become carboxylic acids, and one of them is going to be gone. Right, so the way you can look at it, right, if you don't want to draw the mechanism at this point, you say, okay, I'm getting rid of U, right, because basically both the esters are basically the same, right? It's symmetrical. I'm getting rid of U, and I'm turning U into an OH, or just an H, right? And then you go look for the answer, essentially, at this point. So the answer to this one is, I have C. Right, so you see that CO2, that means all the esters had turned into carboxylic acids, and you lost one of them.